Hello, everyone. Welcome to another Zoom-esque lecture. Today we're going to be doing resonance again, basically the same thing that we did last time, but we're going to be doing complex numbers. In your homework, you have to do both derivations, and then in the final, again, you guys are going to be able to choose which one you want to do. So you just have to derive the resonance motion, and you can do it whichever way you want. So you have to find A and phi whichever way you want. So let us see. Let me find my notebook where I want to be. Okay, so yes, so just as a reminder, last time, and I have the slides from last time over here, just in case we need them, but in fact, I'm gonna actually, give me 1 second. Okay, good. So last time we found that we had a driven damped oscillator, right? And so we had a spring force minus kx, plus we had a damping force, that's minus bv, and we had a driving force with an amplitude f naught, and it was a cosine of omega t plus phi. No, there's no phi there, sorry. This was the sort of sum of forces that we had last time. And so if we did F equals ma, we found that we had an equation of motion that this led to. Can I just move a little arrow? We found that this led to, okay, it was x double dot plus 2 gamma x dot, let me get rid of all this stuff, plus omega naught squared x equals little f naught cosine of omega t. This is what we found last time. This is the equation of motion of our system that we were solving, where of course gamma is b over 2m. I won't write it again, but I'll just say it. Gamma is b over 2m. Omega naught was square root of k over m. So of course omega naught squared would just be k over m. And f naught, little f naught, was the reduced driving amplitude, which is just f naught, big F naught, divided by m equals little f naught. And of course, omega is also a known value. This is just a driving frequency, okay? So we had this, and we found that the solution, or a solution rather, was of the form, just again, boop, of the form x of t equals a cosine, move this down, a cosine of omega t plus phi. And we found that the frequency of the solution is always the frequency that we're driving it at. Always, no matter what. What changes as we change the driving frequency or the driving amplitude is the amplitude of the oscillation motion, or the phase of the oscillation motion, which is measured relative to the phase of the force, basically. So here we have the force with 0 phase, so that we just have the phase between the two guys here. So that's what we kind of found last time. So we're going to basically do this again. We're just going to do it with complex numbers. And so how are we going to do this? Let me just write that first. Let's repeat this procedure with complex numbers. Start from the equation of motion. So remember, when we were doing complex numbers last time, we had to somehow turn, right now x corresponds to the position of our real particle, right? If that was a complex number, that would be meaningless. Like we can't translate a complex number into a position in real space. Like that doesn't have any meaning as far as we've described it in our mathematical model. So what we have to do is we have to find a way to use a different variable that is complex, which we call z, and we have to build it out of x such that when you take the real part of z, you get x. So the way that we do that is very similar to last time, right? So we introduce another real variable y that follows the following equation. It's the same equation. I'm just going to write it. Y double dot plus 2 gamma. It's not actually the same this time, Doug. 2 gamma y dot plus omega naught squared y equals f naught. And remember last time it was equal to 0 and it was just exactly identical. But this time we're going to do it a little bit differently. When we define this y, remember we can define this y however we want. We're just making something up so that it's useful, so that we can make a useful analogy to complex numbers. We can write whatever we want in this equation. I could write t squared. It doesn't matter, right? Like this is just something I'm making up to make our lives easier by being able to use complex numbers. If I use t squared here, it wouldn't actually make our lives any easier. Also, that would break units, right? That wouldn't make sense with the units because cosine is unitless. So, well, yeah, that wouldn't make sense with units. Actually, that could make sense. You would just have to change the units of y. But anyway, what we want to do is we actually want to use a sine here of omega t. And we're going to see why we did that in a second, right? So, and what we're going to do then is we're going to take this equation and we're going to multiply it by I. So we're just going to multiply every term by I. There's going to be an I here. There's going to be an I here, here, and here. So now, we can add together both of our equations. This is just like we did last time with the damped harmonic oscillator. And if we do that, we will find that we can write this as x double dot plus iy double dot plus 2 gamma x dot plus iy dot plus plus omega naught squared x plus iy equals, and here we're going to have f naught. Let me make this a little bit smaller so we can fit more stuff in here. F naught cosine of omega t plus I sine. Maybe you guys are seeing why I did sine instead of cosine. Sine of omega t. Or maybe not. That's fine too. So this is our equation. I'll make it big again because it didn't really matter. This is our equation, right? So I'm going to do two things. First off, we will define a new variable z, just like last time, which is going to be equal to x plus iy. X plus iy. And z is a complex number. So z is in, how do you write the complex numbers? Oh gosh. I don't know how to write that thing. Letter-like symbols. What do we call this? Double C. Okay, hang on, let me do that. Double C. There we go. Z is a complex number. That's what I just wrote here. Yes. So we we will use Euler's equation to rewrite the force side. So we're going to end up with Z double dot plus 2 gamma Z dot plus omega naught squared Z equals F naught. And we're going to write this as e to the I omega t. Does that make sense? Because this, from Euler's equation, cosine of something plus I times sine of that thing, is just e to the I that thing. Okay? So here the thing is omega t, right? And so this is the complex equation of motion. And notice that there was a little bit more nuance than there was before because we'd used a sine here instead of a cosine. We didn't just copy the equation with the y. We actually have the same equation, but sort of moved 90 degrees ahead in phase. And that actually it makes perfect sense. We actually could have used any sine function here, any sinusoidal function here, and just sort of shifted it left and right. That would have been okay as well. It would have just made the math a lot uglier. And since we're trying to make our lives easier with this and we can pick whatever function we want, I picked the one that makes everything the nicest, which is sine. So, okay. We literally could have also set this equal to 0, and I think it would have still worked. But again, that would have been worse. So the whole point of this is to make it all easier. Okay. Now we simply have to solve for z of t, and we can then find our position as x of t is same as before, the real part of z of t, the real part of z of t. All right. Same as before. Are there any questions? Can we get a quick pause on the video and just do a quick questions check? All right, I will assume you paused the video. So, you guys might remember from when we did this for the underdamped oscillator, the next step is to solve this, and we do that by making a guess. And you might be wondering if our famous super guess is still relevant here, and I'm happy to report that it is. So let me grab this, move it over here. So this is our equation of motion that we're trying to solve. And we're gonna make, we will make the same ansatz, why is that capitalized? Ansatz as before. We're going to assume that z of t is of the form a tilde, oh, does this work? Yes, a tilde e to the I, sorry, e to the lambda t. Where a tilde and lambda are both complex numbers. Let's say are both allowed to be complex constants. All right. Well, we want to plug this in. We have to calculate the derivative. So, of course, z of t equals a tilde e to the lambda t, z dot of t equals a tilde e to the lambda t, but there's a lambda in front, and the double dot version, of course, z double dot, oops, z double dot doot, z double dot dot. Okay, is lambda squared. Sorry, typing is hard. Okay, I played that that typing game that you guys told me about. The was it Amandeep that told me about it? It was like a monkey keyboard, monkey type. I think it was, yeah, monkey type. I only got like 65 words per minute. I'm actually really bad at typing. So yeah, that's sad. Anyway, okay, so these are our this is us just calculating derivatives so we can plug it in. And when we plug it in, we're going to find, right, we have our function up here, our equation up here. That was going to be lambda squared a tilde e to the lambda t plus 2 gamma lambda a tilde, oops, tilde e to the lambda t. Okay, I'm sure I'm boring some of you guys. Omega naught squared. Just bear with me. A tilde e to the lambda t. Okay, equals f naught e to the I omega t. If you guys know what's going on and are getting a little bit bored, just try getting ahead of me, right? So just try getting ahead of me and see how far you can get. Omega t, just so that you don't get bored, I think. So that's what happens when we plug in. We get this expression here. So, as always, we're going to group together everything that depends similarly on t. And luckily for us, everything has an exponential dependence on t. So we're going to group all of that stuff together. And we're going to find, oh gosh. So, yes. Okay, we're going to find, let me write it like this. A tilde times lambda squared plus 2 gamma lambda plus omega naught squared. Is that right? That is right. Times e to the lambda t minus f naught e to the I omega t equals 0. Okay, so here we have two different functions, which in principle could be equal to 0. Sorry, we have two functions here, e to the lambda t and e to the I omega t, and in principle they could be different, right? We don't know that they're the same thing yet. Spoiler, they will be. But what we have to do then is if they're different, then these are two different dependencies on time, right? And so their coefficients, in order for this whole thing to be 0 at all values of t, then their coefficients must be 0 at all values of t, right? So that would tell us two things. That would tell us that this whole thing has to be 0, which is true, but it would also tell us that f naught has to be 0, which is not true, right? F naught is given constants, and the constants are not 0. They don't have to be 0, right? We could have some driving constant, some driving force. There we go, that's the word. So the only way this can work out is if these two functions are actually the same thing, and this f naught is part of this whole stuff that's written over here, right? So these two functions must be the same. The two functional dependencies on time must be the same. So that means that e to the lambda t, lambda t has to be equal to e to the I omega t. Or in other words, lambda equals I omega. Okay, so we found one of our constants, right? This is one of the, remember that we had our guess, our ansatz looked like this. And we've just found one of the values for the constants in it that we didn't know beforehand. We still have to find a tilde though. Okay, great. So if lambda is e to the, if lambda is just I omega, then we can group all of these things together. And I'm going to go ahead and do that. Move this over. Here's this guy. And this f naught just gets sort of absorbed into everything else. Lambda is I omega. I'm just going to write it as I omega. And there's a minus f naught in here. Okay. Sick. And also, we know that lambda is I omega, so why don't we go ahead and plug that in everywhere? So if you take I omega and you square it, that'll give you minus omega squared. The minus comes from the I squared. What else? Oh, why are you not working? Oh gosh. Okay, yes. Okay, and this one's just going to give us I and an omega. And that's it. Those are all the lambdas in here, okay? Great. So what does this tell us? Oh, and I made a mistake. I made a mistake because I can't just bring f naught into this parenthesis because there's also an a in front. So this is actually a f naught over a tilde. That's my bad. A tilde. Okay, that makes sense. Yes. Okay. So now that we did that, we can basically, all these factors on the outside, we can just divide both sides of the equation by a tilde times e to the I omega t. And because there's 0 on this side, it won't do anything to that side. So let me do that over here. We're going to get nothing there, and we're just going to have this whole thing. There it is. All right. And from here, we can solve for a tilde. And if we do that, I will just tell you guys the answer. Won't make you guys watch me do more algebra. A tilde. Why is that A not curly? Hang on. There we go. A tilde equals, what do I have? I have f naught divided by omega naught squared minus omega squared plus I times 2 gamma omega. Okay, what is going on right now? Let's take a step back. Let's figure out what's going on. Just mark this with a little square. Boop, boop. Okay. All right, that's a tilde. So we found our solution. Let me just write down our solution real quick for z. We found that z, why is this so small? There we go. It's just going to be a tilde, which is this whole shebang over here, times e to the I omega t. I omega t. All right, that's our complex solution of to the motion of the system. Okay. All right. So hold on a minute, right? Because when we did the other one, when we did it with the real numbers, which was maybe more intuitive during the whole process, we had to find a, and a back then was a real number, and it looked like this. And we also had to find phi. So how come now we just had to find a only? Like what really happened with the whole phi thing. Lambda, by the way, lambda is just because I was being general. In the first case, when we did it with real numbers, I could have said I don't know the frequency of the solution, but I kind of just said it was going to be omega from the beginning. Where is it? Where's my guess? Here. At the beginning, I already said it was going to be omega, whereas here, when I was doing the complex solution, I sort of called this number lambda, which is why we had to also find lambda, whereas last time we didn't have to find that. The point is, like last time we had to find the amplitude and the phase. Why did we only have to find the amplitude this time? And it's because this is a complex amplitude. It actually has two components. It has a real part and an imaginary part. Or if you prefer, it has a magnitude and it has a direction, right? It has a phase. And precisely the magnitude of this number is the old A that we found last time. And the phase is this one, this phi over here, right? So that's the deal with A, right? So A actually contains both the amplitude and the phase in it because it's a complex number. It can carry more information. Okay? All right. So let's see if we can write it more explicitly, right? Because, of course, the next step is to take the real part of this. But, yeah, we want to sort of get the phase explicitly so we can move everything into an e to the I omega something, e to the I something. And then when we take the real part, that'll just all go together into a cosine. Okay, I'm going to make some room for questions right now. Does anybody have any questions that they would like to discuss? And you can go ahead and pause the video if it's all. Okay. Great questions, everybody. I assume, I hope. I wish I could be there. But okay. The next thing that we want to do is take this number down here, right? Okay, so we want to write that. Okay, let's. Okay, what do we want to do? We want to. Now we want to find x of t, which, as we know, is the real part of z of t, right? So let's go to a new slide. All right, let me just copy down z of t from last time. Z of t was this. So let's see what's up. Okay, so that's z of t. Why don't we take this whole part and let's write it in polar form, right? So let's write it as a real number times e to the I something, okay? Okay, now there's multiple ways to go about this. The first thing you might think of when looking at this is, okay, I have to get it into Cartesian form because right now we have something over something plus I something, right? So you'd have to get this complex number in the numerator, and you do that by multiplying by the complex conjugate, right? On the top and then the bottom. That's how you move this I stuff up. And then you would have it in Cartesian form, and then you can just do the sort of transformation to find A and to find phi and whatever. Okay, that's one way to do it. There's a faster way, and it's instead of working with this whole number, let's just turn this into a polar form, and you guys will see why. Because once this is in polar form, all the complex stuff can move up really easily. You just have to flip the sign on the exponential, and it moves right up. So we don't have to do that whole complex conjugate thing. So let me show you guys what I mean. So let's make this number. Let's write this number in polar form. Okay, so if we do that, well, it's in Cartesian form right now. So we have to take the amplitude, or the number that goes in front. Okay, it's going to be something, just to remind you guys, something times e to the I something. That's what polar form looks like. So the first thing is going to be the square root of the real part squared plus the imaginary part squared. The real part squared is going to be omega naught squared and you know what? Give me 1 second. How did I write it last time? I want to make sure. Okay, I wrote it as omega squared minus omega naught squared. So let's actually keep that. So I'm gonna go ahead and change z. So I'm gonna make this omega squared, and I'm gonna make this omega naught squared, and then I'm gonna add a minus sign to this part over here. I just flipped the order, added a minus sign, right? That's all I did. So if we square this whole thing, that minus sign goes away. So it's going to be omega squared minus omega naught squared squared. That outer square is the reason why we can get rid of that minus sign. And then we have the complex part, which is just 4 gamma squared omega squared. That's this. That's the amplitude. Now we just need to do e to the I, and I'm gonna write e as exponential function. It's the same thing. Let me just make a quick note. Exponential of x of any number is the same thing as e to the x. It's just different notation, which instead of having to write a bunch of tiny subscripts, when you have a lot of stuff in an exponential function, I prefer to write it like this, so it's like bigger, you know what I mean? So we're gonna do that. So it's gonna be exponential of I times the arctangent, boop, 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 arctangent of minus 2 gamma omega divided by omega squared minus omega naught squared. Good. Okay, this is huge. This is massive. I'm gonna move that down a little bit. And maybe I'll do this. Okay, good. So this is our z of t. This is z of t. No, I lied. This is the number. This is the number in the bottom. Sorry, this is this number here that I just rewrote. This is the polar form. It looks kind of gross, I know. But now that we have that there, if we put this in this denominator, right, then this real number just kind of goes with the f naught up front. And I just do that. Here is z of t again. Z of t is going to be f naught divided by, so here's the amplitude. It just kind of hangs out in front, which will be down here. And then we're going to have e, I'll use exp again, exp of. So we had this I omega t from before, I omega t. And we also have this arctan thing, arctangent of all this shebang. Arctan this. Okay. Oh gosh. Good Lord. Okay, there we go. Okay, and we just did the same thing. This is just the same. Oh, I'm sorry. This shouldn't be z, should it? Wait. Oh, yeah, it should be. Sorry. Yeah, this is z. So, in other words, another way to write this is z of t is a e to the I omega t plus phi, where a equals all this and tangent phi equals all this So this is kind of what we were looking for. This should look familiar. This is what we got last time. Okay. This is exactly what we found last time, the a and the phi. And all we have to do now is take the real part of this, which because this a, which by the way is not the same thing as a tilde. A tilde is a complex number. A is just this real number, which is the amplitude of this of z. So you know, a without the tilde is the amplitude or magnitude of a tilde, if that makes sense. So what was I saying? Oh yeah, so now it's very easy to take the real part because we have a bunch of real stuff in front and then e to the I something. So this e to the I something is just going to turn into a cosine when we take the real part. So let's do that. And of course, you guys can already see, you're going to get exactly what we got last time. So x of t, why are you small? Why are you small? Get back here. Okay, x of t equals the real part of z of t, which is the real part of all of this. Let's just call it a e to the I omega t plus phi. Where a and phi are down here, right? So I just don't want to write the whole thing again. And this is easy to calculate. This is just going to be a times cosine of omega t plus phi. I'll just write it. Omega t plus phi. That's it. And that's exactly what we got last time. Last time we had precisely this. Ta-da. All we did was we used complex numbers to do the intermediate steps, and we found this. So when was this easier exactly? I hear you asking, like, when was this actually worth the whole complex number thing? Number one, taking derivatives was a lot easier. If you understand the other parts, and maybe they're not like a lot of work for you, like dealing with complex number algebra, you're fast at that. You know, the thing that would slow a physicist down instead is taking these derivatives. You know, so I mean, it doesn't take that long, but these derivatives are much easier to take than, where are they? Than these derivatives. I mean, not that much. They're not that much easier, but they are easier. And then if you do it this way, right, when you plug everything in, you have cosines, you have sines, and then you have to do this ugly, ugly thing. You have to split up the angles. You have an omega t plus phi inside the cosine, so you have to write that as a sum of angle formulas. And then you have to group everything together by cosines and sines. Like the algebra, which I actually just skipped last time, was very hairy. Compared to the algebra you have to do here, there's just some real number taking at the end. So it's stuff like this. But this is not, it's not that bad, in my opinion. I don't know. It's really up to you guys, which is why, oh, and I should have a parenthesis here. That's my bad. Should have a parenthesis. Wait, should I? Yes, I should. Come on, parenthesis here. Yes, that is my bad. Anyway. Yeah, so this is my preferred way of doing it. But if you guys don't prefer complex numbers, or you don't want to learn them right now, or you don't want to deal with them, that is fine. You guys can just basically forget this if you really, really want to. But you will use it in the future. So, if you're doing engineering or physics, so your choice. So this is the complex number approach. This is how we derive these same things using complex numbers. Okay, so let's actually, so I'm going to spend the next like 20 minutes just sort of showing you guys some stuff on Desmos to help you guys build intuition. I think I'll share this Desmos file with you guys that I made eventually, but I was trying to find the source of the word sine. So is this the right one? No, this is the one from last class. I think it's this one here. Okay. Yes. Okay, so what's going on here? So I want you guys to imagine that this is the complex plane. So the x-axis corresponds to the real part of this complex number. You'll see it skip every once in a while. That's normal. It's just because of a limitation with Desmos. So this x-axis is the real part of the complex number, and this y-axis is the imaginary part. So this point is a complex number. It's not just a real number, it's a complex number. And you can see that it changes over time. So I want you guys to imagine that this is the driving force of our system, okay? So remember that our driving force, if we go back to our presentation really quickly, we were able to write it as like this. This is called the complex form for the driving force, right? Instead of f naught cosine of omega t, like we had it here, we have f naught e to the I omega t. It's just a complex form. If you take the real part of this, you get back the original force, okay? So here it is. If I make f naught over here in the corner, if I make it bigger, that increases the radius, because that's what the amplitude is. It's just f naught. And if I change the frequency, omega, then it'll start going around faster. While I'm changing the frequency, ignore that weird stuff it does when I'm changing this number. That's not physicsy. That's just me changing the number and Desmos adjusting, but don't read into that. So here's a high frequency, here's a low frequency. Makes sense, right? Okay. So this is the complex force. Now I'm going to add a drawing for Z, which is our solution. Okay? So here's our solution. And I'm actually going to go to really low frequency to start. So here's a really low frequency. Okay. So first of all, our solution Z of t is in units of like meters or distance or whatever. So, and the F is in solution of like newtons or forces. So don't compare the lengths of these guys, because that comparison doesn't make any sense. They have different units. You can't compare them. But I do want you guys to compare the angle, the phase that these complex numbers have, right? So at very low frequency, when omega is very small, these two guys are basically in phase. They're moving together, right? This angle between them is basically zero, right? And actually, if omega were zero, then the angle would be exactly zero, but that doesn't make any sense because they're not really oscillating. So this is kind of what you see, okay? So as I start to increase omega, I'm actually going to introduce this omega slider, just so we can do it on the screen. Yeah, this is just me moving omega up. It's borrowing the axis that I used for the real part, but in reality, when I move this point, this is the value of omega. So here I am moving the value of omega. Notice two things. First of all, the amplitude of the solution of of Z of t is changing. We're getting a bigger amplitude. And this angle between the motion of the oscillator and the force is increasing, okay? Let me say one more thing. Z of t, which is this red line, how do you see the motion of the oscillator here? Well, it's the real part of this guy, right? So it's the x coordinate of that point, which, as you can see, goes up and down. It goes in sinusoidal motion, okay? Now, as I keep increasing this frequency, you can see that the amplitude of x, like the length of that red line, is getting longer and longer, and the angle is getting bigger and bigger. And here the angle is 90 degrees. So it's kind of like x is lagging behind the force by 90 degrees. That's kind of what we mean. And as we keep going, now the amplitude of Z of t starts to decrease, and the angle continues to increase until at a very high frequency, they're basically opposite each other, right? So their angle is like pi, or 180 degrees, and x is really small. X goes to zero. It actually becomes just a little dot as we keep increasing the frequency. All right. So I assume that a lot of you guys understood that what we were seeing was we were sweeping frequencies and we just went over a resonant peak. Okay, so let's actually see that now. So here is the amplitude of Z. This circle represents basically the amplitude of oscillation of Z, and I'm going to change some parameters here. Let's make this like this, and let's maybe decrease the damping a little bit. So here, as we continue to increase omega, you can see that for low frequencies, these two lines are basically together. Maybe you can't see that. Let me make this big. No, that doesn't help. Okay, well, these two lines are basically parallel, but as I continue to increase, the angle increases, and also the magnitude of x increases to some maximum here. You can see that I have the plot of A of omega here, and then it starts to go down. Okay, goes to some maximum, and then it starts to go down. So that's what's going on over here. And then if you go way to this limit, they're basically opposite each other. If you zoom in, you can see that, right? The angle is like 180 degrees, and the amplitude keeps decreasing and decreasing, which you can also see here on this red line, going to 0. Boop. All right. So we're looking at things in the complex plane because it kind of helps us visualize a little bit. But if you ever want to think what's actually going on in the real world, just sort of take the projection of these lines to the real axis. And that tells you what the real values are of these two guys. But it's just really helpful to see things in a circle because you kind of see them moving together. You see that this angle between them is constant. It's a nice visualization. So we can also see here, this is the phase of, this is basically the angle between these two guys, right? So this is kind of how far ahead is the oscillator with respect to the force. And of course, it lags behind, which is why this angle is always negative. So the force is, the position is always trying to kind of follow the force around. And so it can lag behind really closely if you have low frequencies. And as you go past the resonant peak, it sort of goes past 90 degrees very quickly, and then it goes to 180 degrees over here. 90 degrees at the resonant peak, and then back to 180 degrees. So one thing to mention, you might be saying, oh, okay, so the resonant peak is exactly at 90 degrees. That's not actually true. The resonant peak from last time, if you guys remember, was at, what was it? Square root of omega naught squared minus 2 gamma. Oh, you don't have gamma, that's true. Gamma squared. And this is the resonant peak. If we put omega to be right there, come on, right there, then you can kind of see it. The angle isn't really 90 degrees. It's a little bit less. Let me maybe stop the timer, stop the time, and we can see that more clearly. See how that angle is not quite 90 degrees, right? So 90 degrees is not at the resonant peak, and the resonant peak is not at 90 degrees. 90 degrees actually happens when the frequency here is omega naught, right? So where's omega naught? X equals omega naught. Slightly to the right. Slightly to the right. So let's move it over there. Omega is now omega naught. And now if we look at this, then it should be 90 degrees. And let me see if I can change the time a little bit so we can compare it with the axes. Yeah, you can kind of see it there. Yeah, it's 90 degrees, almost. So, or exactly if I was exactly on omega naught, which I don't think I am. Okay. So this is just a complex visualization of what's going on. I might ask you guys about this visualization on the final. I'm not sure. Just try to make sure it makes sense. Right. All you kind of have to think about is the real motion and the real force are just the projection to the x-axis of these two guys. All right. So that's what we're going to be using. Okay, so for these last 10 minutes that we have, I'm going to just sort of do a little introduction for what we're going to do next class. I'm actually going to get started on the topic that we do for next class. So let's see. I don't know if you guys can hear my laptop going off. I don't know what's going on with it. I think it's just hot in here, but whatever. Okay, there's been something that should be bothering you, right? And it's, well, let's go back to the simulation. Here's a simulation way down here, harmonic oscillator. Here's our simulation. There's a driving force in red and there's the motion in white. And like I said before, this motion does not look like a sine curve. There's more to this motion than just a sine wave, right? Over time, it becomes more and more like a sine wave until it becomes pretty much exactly a sine wave. But like if I disturb this guy, like that's not a sine wave. That's like a sine wave that's moving up and down and stuff, you know. So you might be wondering, like, what's really going on here, right? Like, how can we understand this? Looks like a really complicated motion, and what's actually going on? And the answer to that question is actually pretty simple. It looks extremely complicated, but it really isn't. You guys basically already know the answer. So let's look at the equation of motion one more time, and I'll just argue from the equation of motion. It's quite simple. So this is how our system moves, okay? How did the how did the undriven but still damped oscillator equation of motion look? How did that look? Do you guys remember? What did we ignore this stuff? What did we have to write? Right? When there's no driving force, we still have damping, we still have a spring. What did that equation look like? Well, it's basically just a special case of this, right? If we set the amplitude to 0, then that's the equivalent to having no driving force. And this was the equation that we had. So let me make a statement, okay? So I'm going to call this, so I'm just going to call that x. I'm going to call this x, what do we say? No driving. No driving. No drive. Let's just do that. X, no drive. And these dots are going to be all over the place. You have to excuse that. Can I make it not do that? X. Oh, I can. Fantastic. Let me do that because this looks ridiculous. X, no drive. X dot no drive. And this is going to be, hi Marcus. He always shows up for class, doesn't he? And this is going to be X no drive. Okay. So this is this X no drive of t, this is a function of time, and it describes an undriven oscillator. It's a different problem from this one, and you can tell because the equation looks different. So it moves differently. Okay. However, right, let's say that I have, let's say that I call this x1, x1, x1. Okay, here's my claim. Claim. If x1 is a solution to the equation with driving, which just from having written it here, it is, right? That's what that mathematically means. And x no drive is a solution to the equation without driving, then x1, I'm going to call this x2. x2 equals x1 plus x no drive is also a solution to the equation with driving. Okay, I'm going to ask Vital to pause the video and have you guys explain why that is. And I know somebody here can do it. So, yeah, go ahead. Pause the video. Okay, I assume the video was paused. I assume you guys figured it out, so I'm going to be quick. Right? If we take this, okay, let me take the equation with driving here, and let's just plug in x2. Here's this guy. That's way too big. Here's this guy, and we're going to plug in x2. When we plug in x2, this equation is linear. Okay, this equation is linear. So that means that I'll do it the long way. I'll do it the long way, guys. Oh gosh, sorry. x1 plus x. Man, you guys already know where I'm going with this. You solved it yourselves. You guys solved it yourselves. You're gonna get the same. You're gonna get this. This is what you're gonna get. This is what you're gonna get. Ready? I'm gonna show you guys. Oh god, it doesn't go any further back. Get away. I miss my blackboard. Okay. Okay. We're gonna get this plus this. That's what happens when you plug in x2 into this equation up here. Okay. And put these in parentheses. And I'll put this in parentheses. Okay, well, by definition, all of this, right, which is exactly the same as this, is equal to f naught cosine omega t. That's like that's what it means to be a solution to the driven equation, right? So all of this is equal to that. And then all of this stuff is equal to 0. So the equation is still true, right? If we use x2, this solution that's a sum, the equation is still true. Because the undamped motion is equal to 0, so it just kind of like goes away if you plug it all in. And it has to do with the fact, again, that this equation is linear. So it means that if you have one solution to it, then the solution with 0, which is called the homogeneous solution when you study differential equations, like without any time dependence, that solution is also going to be, you can add that in, and it's also going to work. So what's actually going on? Well, there's two solutions. There's two types of solutions almost. So let me move this over here. In reality, there's two types of solutions. Well, okay, hang on, sorry. Let me fix that. There's two solutions added together. There's two, let's do this. Let's do behaviors. Behaviors added together. Undriven motion, which is transient, meaning it goes away, it dies out over time, and driven motion, which is steady state, meaning it doesn't go away. The undriven motion we already studied. That's just a damped harmonic oscillator. The driven motion, that's the new stuff that we figured out. So the full solution to the motion of a driven oscillator is of the form and now we basically bring back our old friend, the undriven but still damped motion. There's two cases. There's under damped and there's over damped. I'm only going to write the under damped. I think you guys, well, let's see if you guys can understand. So we're going to have A cosine. Should I not call this A? I'm going to call it A naught cosine of, and the frequency here was square root of omega naught squared minus gamma squared times t plus phi. Yes, plus phi naught. This is the underdamped equation of motion. This is basically how an underdamped oscillator moves. Plus, right? Plus a cosine of omega t plus phi. Where, let's describe these different a's, where a naught and phi naught are determined by initial conditions and A equals what we found already, which I guess I can copy. You guys have it already. I'm just gonna write it down for completeness to be nice. A is this whole thing, and tangent phi is this whole thing. This is what we found earlier. So you just you take the steady state motion plus the what do you call it? The transient motion. Okay, so that's kind of what goes on, right? So if we go back to our simulation really quickly, the initial conditions, right, where I put this thing, that determines this kind of initial underdamped motion, but that dies out over time. If you just imagine seeing that on its own, and let's just do that. Let me turn down the force amplitude. That stuff goes away. That stuff dies out. But the full solution is the sum of this exact motion plus the steady state one. So it leads to this sine wave with a smaller sine wave that's dying out on top. That's exactly what we wrote down here. Oh, I'm sorry, I forgot something here. That's totally my bad. Maybe some of you caught this. This should have an e to the minus gamma t. Otherwise it doesn't decay, right? That's my bad. Boop. And this is x of t. This is the full solution. X of t. Why are you weird? X of t. Why are you weird? X, there we go, of t is this whole thing. This is the full solution. So I'm gonna mark that, and then we're gonna be done for today. So please hang out, work on the homework, or I don't know, or leave if you really want. I'm not your father. Although I think I have permission to tell you to stay. But I don't know. I recommend you guys work on the homework. That's all I'm gonna say. Whatever, I can't figure out how to double outline. Okay, that's all we have for today. If there's questions, please ask them. And yeah, I'll see you guys on Friday remotely. And yeah, have a good rest of your day and Thursday. See you guys.